So these Fridays Transmitting Seminar Series are co-organized by the Department of Civil and Environmental Engineering and also the Kardar Center for Urban Transportation Research, and also is co-sponsored by the IT student chapter at the USF, and also co-sponsored by several USDOT University Transportation Centers, including the CTEC, NYSER, and TOMNET. And today we are very glad to have Professor Jorge Lava from Georgia Institute of Technology to give us a talk on the traffic flow theory. And Dr. Lava, he received his doctoral degree from UC Berkeley in 2004, and from that time I was a graduate student over there, and Dr. Lava worked as like a postdoc for two postdoc positions. One is the at the Institute of Transportation Studies at the UC Berkeley, and then he went to French National Institute for Safety and Transportation Research, and then he joined Georgia Tech, and his research interests mainly in the traffic flow theory and simulation modeling, and in particular, I think in the congestion in urban networks, and he has made a significant contributions in traffic flow theory, and I think freeway capacity and ramp metering strategies, and relationship between the driver behavior, human factors of drivers, and the on stop and go traffic flow pattern. And also he made contributions to the congestion pricing, and also the machine learning models for congestion control, and along that line. So, and as you may also know that Dr. Lava was the major advisor of Professor Hao, who's the new faculty member within our department. So with that, please join me in welcoming Dr. Lava.
Thank you. Thank you very much for the kind introduction. And thank you, Carl, for this great invitation. Yeah. All right, I'll jump right to it. I have lots to tell you. So what I'll be talking about today is my latest research during the last, I don't know, 3 years or so, where I realized that all I've had learned so far is not really helpful for the types of problems we want to tackle here, right? So most of the material is not going to be familiar to civil engineers. So it's kind of a warning. And that's kind of the main finding, right? What I found is that the tools we're used to using in our field, and not only in traffic flow, just in all branches of civil engineering, or engineering really, all the important problems are based on, or they all have in common this complex systems, I'm going to call it today, complex systems nature. Okay. Traffic flow is just one problem that has this nature, let's say this characteristics, but also earthquakes are complex systems. You cannot predict when the next earthquake is going to come, right? Or the stock market, when is the next crash going to come? Where is the stock price going to go up or down, right? Those are things that are unpredictable until now, right? Nobody can predict those things. And the realization from this work is that the reason for that is that this is a chaotic, complex system, okay? So, yeah, it's not going to be a very uplifting seminar in the sense that I'm going to raise more questions than answers, right? All right. So these are the main messages of today. Right, what I told you, traffic flows is in the same family as all these systems, right? Earthquake, stock market, forest fires, spread of epidemics, the collapse of networks, network blackouts, right? So all the problems are challenging today in our infrastructure systems, and natural system too, right? Fall in this category. And yet, in engineering, we don't give you the tools to analyze the systems, okay? All right. The other big message is that complex does not mean complicated in my talk. Complex is just what appears to us humans to be complex. You can start with very simple rules. Very simple rule, which is traffic. Traffic is very simple. You know, a 15-year-old can drive, right? I'm teaching my kid now how to drive. And it's just brake or go forward, right? So it's a very simple process. Yet we're going to see very complicated things when we measure traffic, right? All right, and these are more examples of complex, the type of complex systems, right? And these are all unpredictable systems. So if you want to predict the dynamics, then you can't do that. Okay. And there's other methods, there's other questions you can ask of all these systems that are relevant, right? But if you don't know that they're unpredictable, and then you insist on predicting them, I think that's the story of our field in the last 20 years. Okay. Other big message is that the models we've been using, which are typically meso or macro, because we cannot model big networks, right? I mean, there's people that say, yeah, put more compute in, and then, yeah, we could probably model a whole city, but that's not the case. I mean, maybe you can do one run in real time, but if you want to put dynamic assignment, traffic assignment, right, then you might need supercomputers, and maybe even if you have those, you won't be able to do it. Right, so we've been using these type of aggregated models, again, because we cannot do the real thing. And therefore, we're missing out on all these I'm going to call it criticality or complex nature. Right, so when you use these models, you don't see the problems that arise in reality that are due to criticality. Right, it's like the models that we use, like they they soften, they make all this continuity smooth, right? That's why they're messy, because they take some sort of average at one point, right? We're not modeling individual drivers. We're modeling maybe platoons or drivers, or an aggregate. And whenever you do that, you're going to lose criticality. So to me, that's the main explanation for why we haven't noticed this problem before, right? It's because we've been using the wrong models, right? If you run these models, you're never going to see a chaotic system. You will always be able to predict what's going to happen, right? That's because we're using the wrong models. All right, and I'm going to come back to this concept of spatial clusters, which really it's at the base of all these problems. All right. Talk about some implications. The first one, I think we need to change the paradigm. Right, I think insisting on predicting the unpredictable is not the right approach. We have to change our models. And yeah, what we're saying is that we need to use microscopic models, not meso or macro, right? Which is very challenging, right? We don't have the compute yet, but okay, that's the nature of the problem. Right? And all we teach you guys, it doesn't work in the real world. And this is why. Because of chaos. Criticality is, I'm going to call it the same. Okay, so let me flash a few pictures and go down this list. Yeah, so this book, if you want to get started, I mean, it's really good. I mean, these three concepts are the same. They're synonyms in a way. One comes with the other, right? You hear fractals, they're going to be power laws, and it's going to be chaotic, right? Again, don't feel bad if you don't know what fractals are, and again, it's because we don't teach. But yeah, probably you've seen these type of pictures and you have an idea of what they would be, right? All right. So whenever we have power laws is the opposite to the normal distribution, right? The normal distribution is, again, what we teach you guys the world is, because of the central limit theorem, right? And we overuse that theorem. We think it's true everywhere, right? We think, yeah, there's just take average, so it should be normally distributed. It's like a law almost, but it's not. It's not a law. Whenever you have infinite variances in your random variable, then it's not going to be normally distributed, right? The central limit theorem would not be helpful because it would not converge, right? These power laws they all have infinite variance in the type of problems we're dealing with. And in the case of traffic, is the worst case scenario, they don't even have a mean. So that you cannot take the expectation of a power law distribution in the case of traffic. Right, so it's mathematically it's the most complicated problem there is, because I mean there's no mean or variance. Right, I'm sure you haven't heard this before. Because I mean, if you have nothing, what do you do then, right? So that's the challenge that we're facing. But we're gonna try to work around it, right? And the physicists and the mathematicians already dealt with this. That's what they do, by the way. Physicists, all their problems are either quantum mechanics nowadays, right? But all these challenging problems, and they have developed theories and methods that engineers we should be able to use, but we don't, right? All right, so that's the change of paradigm. It's just going back to the original, let's say, definition of an engineer. Use the tools of mathematics and science to the benefit of society, right? And then again, we're not doing that. We're just developing our own tools. And anyway. All right, so most real systems are not normally distributed. The main implication is so typically if it's normally distributed, we would say that fluctuations growth time as the square, but they actually grow as the 1/3 power, and that has many implications. We're gonna touch on those in a minute. All right, for education, yeah, I've been telling you that message now for a while, but yeah, I kind of feel bad that we teach the wrong stuff, to be honest. All right, this is a big one, right? And it's again what we've been trying to do so far: maximize the flow of your system. That's your beneficial. I mean, that's the way of maximizing the benefits. And it's actually not, right? And experience tells us that that's not the case. You always want a buffer in the system, right? You don't want to push it to the limit because it's going to explode. That's what happens, right? Great. So that's a big one too. So only we should use micro simulation models. And an example I'm going to use today is about the superlinearity of the scaling of congestion. All right, but let me go through some of these pictures. Now, why are things not normally distributed typically in our engineering world? It's because we built our roads, for example, on top of a fractal, right? A mountain is a fractal. Therefore, everything that happens on the road should obey the math of fractals, which is not calculus. This gives a little bit of an idea why traffic is chaotic near the critical density. I'm not sure about the background, if everybody here knows what a time-space diagram is or not. But anyway, we're going to have space here, so it's the distance from the beginning of the road. This would be a vehicle trajectory, for example, and we have time there. Right? Right, so this, what you see is the simplest traffic flow model. We're going to call it Stellar Automata 184 today. And what you see here in colors are the waves of traffic, the stop and go waves. Okay, they go against traffic, right? So this is a vehicle trade going downwards or downstream. Right. Congestion propagates in the opposite direction as these, we call them waves, right? And they're parallel like this at the same speed. I'm going to show you empirical data in a minute, but yeah, this is pretty much how traffic is. If something happens at the boundary, at the initial conditions, right, at t equals 0, that's going to propagate. If it's congested, so here you had more than the critical density, and critical density is the number of vehicles per unit distance, right? So on average, it's near the critical density, which is 0.5 here. So there's a little bit more than that, right? And when there's a little bit more, you should expect a congestion wave to propagate in this way. When there's a little bit less than the critical density, what you have is these voids propagating forward. These white spots is just the absence of vehicles, right? So it's the voids that propagate forward in, let's say, free flow, or when you're under the critical density. But when you're over the critical density or in congestion, then you would have these waves propagating back. All right, so what happens is that the sensors we have on the road to tell us what's the initial condition may not have the necessary accuracy in order for us to see precisely what this number is, right? So traffic is a chaotic system, which means that if you change the initial conditions very little, the output of the model when you run it could be very, very different, right? So that means that if you want to be able to predict, you should be able to get a perfect estimation of the initial state here, of the initial positions of every vehicle, right? And if it's chaotic, it means that if you get the position of one vehicle 1 centimeter with 1 centimeter error, that could propagate and make the difference between a free flow state or a congested state. And that's the crux of the problem. That's chaos, right? Is if you change the initial conditions a little bit, then if you run the system long enough, you're going to get totally different answers to the problem. All right, power laws. Power laws are everywhere because all the systems of interest, as I said, are chaotic, complex systems. Okay, but they appear in many common random variables like the populations of cities. So this is France, right? France has 36,000 cities. That's a lot. Anyway, so here you have the population of each city, and here's the probability that the population is greater than something. So we call that the survival function or the complementary CDF. So if it's a power law, it's going to be a straight line here when we plot it on a log-log scale. That's the way to spot traffic power laws in the wild, right? So you plot the distribution function, this one. If you see a straight line, it's a power law. And then the slope is really important. It's what determines if you're going to have a variance or not, or if you're going to have a mean or not, right? So the slope here is going to be 151, okay? Which means that there's no variance, but there is a mean. So if it's between 1 and 2, there's no variance. And if it's below 1, there's no mean either. And that's where traffic is. The slope of traffic is 0.5. Worst case scenario. Anyway, all right, back to our populations. Let's get the feeling of this. So this would be Paris, and maybe Marseille, Lyon, etc. And we see that most of the cities have a small population, right? So they all around this. And then the bigger cities are very spread out like that, right? But yet, you see this power law, right? And if you do it in any country, you're going to find the same thing. The slope might be slightly different, but it's always going to be between 1 and 2. Of course, depending on the country, the year, etc. But it's the straight line, right? Okay. This is like the typical histogram you would have done with the standard analysis of data, right? And this is just the normal coordinates, and this is the PDF, just the histogram, right? So you see all the towns have relatively low number of inhabitants, right? So they're all lumped up here, and there's only a very few, right? Again, Paris, Marseille, etc., right? Now, typically, if you look at this, you say this is an outlier, right? But go tell French people that Paris is an outlier, right? Or tell anyone. It's obviously Paris is part of the distribution, right? It looks as an outlier in our, let's say, in our common view of these random variables. But when you looked at through the lens of complex systems, right, you see that it's not an outlier, right? So you see, complex systems sounds difficult or unattainable, but it's these type of simple tools, you know, that we need to take advantage of. All right, these are going to go faster, right? So any type of wealth, individual income, or income of countries is going to be power law. And yeah, notice this is the worst case scenario. It's like no mean or no variance. And when I say no mean, it means that if you try to compute it, it's like let's go back to the population, right? You take the population and you want to estimate the mean. You want to estimate, for some reason, the average number of people that live in a French city. All right, you take a sample. That's a statistic approach. Take a sample, take the average. That's your best estimator, right? But then hopefully you see the problem of that immediately. That average will differ very much whether or not you have Paris or not in the sample, right? And that's the whole problem of power laws, is that you cannot estimate them by taking samples, because you never know if you have Paris or not, right? So that's why statistic breaks down. And we need to look for other methods. All right, income. Land area. So a city has a certain land area, and power law, this is kind of weird. I don't know what that is. Road length, power law, mostly. All right, and this goes with this comment that we don't need to maximize flow in order to minimize the delays. So what you see here is what we call the macroscopic fundamental diagram of a city. Maybe you're familiar with the fundamental diagram of a single link. Turns out we can define a similar one for the whole city, which is really nice, because then you don't have to do all the network modeling that's behind. You don't need to calibrate ODs or anything like that. If you have this shape, which there are methods to obtain it, then all you need to know is the number of vehicles in the network. So right now there's 100,000. Therefore, my flow is going to be this number, and with those two numbers, you can calculate average traffic speed, travel time, everything. So yeah, the MFD approach is a very powerful tool. However, this is the kind of the strategy that kind of flows from it, is that you want your city to be at the optimal point here. The number of people you should have in that network should maximize the flow. Right? That's kind of the intuition behind that. And that doesn't work here. And I'm going to show it. We call it self-organized criticality. It's like, yeah, you don't want to push the system to the limit because it's going to blow up. All right, and finally, I'll give the example of the scaling of delay across cities. So here we have the population of cities in the US. And here we have the annual delay. So the delay of all commuters during that year in that city. This is taken from the TTI Urban Mobility Report. Okay, and what you see is a scaling relationship because again, it's in log-log plot. So everything would be in log-log plots. And again, what's important is the slope 1.21 here. Okay. Now that 1.21 is really problematic. We call it superlinearly. So linearly would be the slope equals to 1. So if the slope equals to 1, it's like what we're used to thinking, the linear thinking. So if the population size doubles, you would expect the delay to double. Maybe kind of back of an envelope thought, you know? If the size of my system doubles, yeah, then everything should double. Okay. That would be a linear system. And those are fortunately not the case in complex systems. They're either going to be super linear or this is going to be less than 1. So there will be sublinear, right? Okay, so superlinear is not good for us because it means that if you double the population, then the delay more than doubles, right? It grows with a factor of 2 to the 1.2, which is a lot greater than 2. And that means that per capita, the delay increases. All right. And if you think about it, it might make sense, right? If you go to New York, it might take you a lot longer, right, to get around. If you live in Tampa, for example, right? Yeah. So according to this, I don't know the ratio, but the ratio of the population should be like what, 100 or something. Tampa and New York. Yeah. So 100 times the delay. Well, yeah. Yeah. I just took it from the Urban Mobility Report. Said, yeah, Texas puts out every year this report. Right. Yeah, I see. Yeah, yeah. No, they use loop detectors. They're fusing a lot of data, and yeah, to be honest, I didn't dig too deep, but yeah, they've been going forever, and it's a very reputable source. But yeah, you're right in the sense that no, there's a similar curve for fuel consumption. And that might, I think I'm going to share it. It has like a 1.2 instead of 1.1. So it might be that they took this. I don't know. But yeah, I mean, we need to hopefully verify that it's okay. But yeah, I mean, it makes sense. Yeah. Oh, yeah. Whatever the standard definition, I guess, population is. All right. So yeah, let me, because I always run out of time, so I just want to get the main idea here. So we're going to explain this 1.2. All right, so the way it's going to go, it's like this. So it turns out that the delay scales as the length of the system, which is simply the length of the network, the sum of the link length, right? So it's scaled with the length of the network to that power 3/2. Okay, so that, I don't think I'm going to have time to explain where that comes from, but all these ideas led to the realization that the traffic flow model belongs to what physicists call the KPZ universality class, right? Yeah, I'm not going to be able to explain that a lot, but that's one of the implications of belonging to this universality class. Okay, is that in this case the delay should scale with the system size with that power. All right, so this is the delay is proportional to that, all right? Now here we said plus the fact that this is not like mathematical plus, right? This is saying that the length of the roads, right, on a city scales or is proportional to the area of the city to that power, the gamma over 2. All right, so, and that's what this figure is useful here. So here we have the area, and then here we have the population, right? So we're going to have a relationship between the area and the population, and then another one between delay and population, right? And taking this relationship, which is that they scale linearly, right? So 0.99 is almost 1. So that goes here, right? So the area is proportional to the population. That's the last. If you put these three together, then you arrive that the delay should scale as the population to that power, 3/4 gamma over 4. And gamma is the fractal dimension of the network. And again, it's a pity we don't teach fractals, and I'm not going to be able to explain it to you. All you need to know here is that it's related to connectivity of a network, which is a concept we're more familiar with. So the more connected the network is, think of a grid. Grid is the most connected network, planar network. That would have fractal dimension 2. But if you start pruning links, taking it out, then the fractal dimension goes down as well, right? So it's related to connectivity in that way. And it's going to be between 1 and 2, right? Because networks are at most 2 dimensions, but at least 1 dimensional. All right, so, and then we took data from a few papers reporting the fractal dimensions of some cities in the US, and we estimated it to be in some range, and then the formula using that estimated values gives you this range, which is right on with the observed slope. Okay, so yeah, we were very encouraged by this result and by the consequences. I mean, if you're talking about resiliency and want to make cities, more scalable, let's say sustainable in the future, what this is saying is that you should lower this fractal dimension, right? You want this exponent to be closest to 1, hopefully less than 1. That would be great. Right, the bigger the city, the less the delay per capita. But all we can do now is just reduce the fractal dimension. But then reducing the fractal dimension is reducing connectivity, so there's an interesting question there to analyze. So there must be an optimal connectivity and scaling of delays, right? Which seems interesting to investigate. All right, so this kind of suggests that we could design our networks so that they're more scalable, they're more sustainable. All right. Let me, because I have several slides, I need to choose. Yeah, let me talk a little bit about the history of complex systems, and how it relates to traffic. All right, so we can maybe trace it back to thermal back in the 80s, right? Then Poincaré, which started dynamical systems theory with chaos theory and all that, right? In the 1900s, phase transition. So it turns out that traffic, you can model it as a phase transition of a fluid going from liquid to gas. Liquid would be congestion, gas is free flow. Then Mandelbrot, right, who coined the term fractals around the 1960s. This is the KPZ that I talked to you about. So it's all about how surfaces grow. But it turns out in traffic, there is a surface. We call it the traffic flow surface. And now I understand why we did call it that way. It's because, it obeys this growth process of many natural systems. And it's all in the KPZ. So KPZ stands for the authors, Kardar-Parisi-Zhang. This Parisi is the same Parisi that got the Nobel Prize a few years ago, because of his work on complex systems. So that kind of put complex systems on a stronger foundation now with the Nobel Prize, I think, right? We're also connecting this to self-organized criticality, which I want to explain in a minute. The work of Wolfram, the creator of Mathematica and all that, has been instrumental too in some of these ideas. He takes the same type of problems, but in the computation domain. And of course, network science. Okay, so, and then in the traffic flow history, in 95, Mr. Nigel here, they presented all these ideas, more or less. I mean, I maybe added some, recent, in the meantime, there were several developments, but all these ideas that traffic is chaotic and unpredictable and power laws and fractals, it's all back to the 90s. Even they postulated self-organized criticality, right? And then something happened and nothing happened with this theory, unfortunately. Okay. And I think it was something to do with the Berkeley School of Thought that I was there at the time, so I saw a little bit. And it's this fight with the deterministic models and the stochastic models, maybe. So I'm not sure if that's what the reason that this theory didn't progress more over these years. Yeah, finally in 2003, he postulated most of these ideas. All right, D'Aganzo showed that cellular automata models are the same as kinematic wave models. That was really important because it kind of bridges the gap between traffic and physics. CA models are physics models where most of the complex system theory relies on, actually. Right, so yeah, they're kind of one and the same. This is a really important paper, appeared on PNAS, right? Which shows empirical data about these things, right? So they take data from the city of Beijing, and yeah, actually I'm going to show it to you in a minute. And you see these clusters popping out, last predicted by the theory a little bit. All right, yeah, and this has been my latest flow, which I'm not sure I'll be able to describe. I have 5 more minutes, I believe. Is that 15? Okay. All right. Okay. Yeah, I could go on forever. Yeah, which, by the way, I wanted to talk to you guys about these shells. So on my way here yesterday, I stopped by a gas station in Florida, and they have this beautiful shell with these patterns. And yeah, in Juju's office also, I saw some beautiful shells. And most of the shells, the interesting ones, again, you see these power laws and you see these things. So talking here about cellular automata model, okay, a little bit. And that's one example of a very simple program that generates these things. And yeah, they look like some of the patterns here. And yeah, look at that. It's like the Sierpinski triangle. I don't know if you can see it, but I mean, it's amazing. So what Wolfram is saying with those principles that you can read there, that if so basically he says that you need very little to create complexity. You need very simple rules that would create stuff that for us looks complex, but for nature is very simple. It's just those rules. And then if shells can do it, I mean, that kind of proves this point in an intuitive way, right? Right, and that's the main idea, simple rules, right? All right, and the other kind of, what is the same idea of unpredictability, right? I mean, he's saying that because of this, the only way to predict is to run the model, right? If you want to see what's going to happen with this computation in 10 more time steps, there's no shortcut. You have to do the computation one by one. There's the irreducibility, right? And it's what happens in our case. But in our case, it's even worse because we don't know the initial conditions with enough precision, right? Now, suppose if you did know those conditions with perfect precision, then this would affect it, right? This would still make the system. If you want to predict, you have to simulate it. I mean, there's no, right? Now, in our case, again, it's different. We cannot even simulate it because we don't know the initial conditions with enough precision. Okay. So this is a typical CA model. So in the CA model, we start with a row. Here we're starting with a single one, and then all the rest are zeros. In the case of traffic, this is going to be a car. There's an empty space in the highway, right? But yeah, this is rule 30. There's 256 of them, and these are the rules. So you take these cells 3 by 3, 3 at a time. So you take these first 3, they're all empty. You go to this is the lookup table. So you go to this one, and this tells you if you get this, then the middle cell in the next time step, so in the row below, should be also empty, right? So that's why here 3, there's an empty there, right? So you move that stencil until you get here, let's say, right? You have a 1 in the middle, you go here, that's this one, and that's an occupied site, so it's going to be blue in this time step. All right. So these are the simplest cellular automata. Well, then elementary cellular automata. And there's only 256 of them. But you see how simple they are to program or think about, right? And yet, what you see, it's unpredictable, right? Maybe at the beginning, yeah, you could predict, but if you run it for more time steps, you start seeing more intricate patterns. Right? So here it's easy to predict, you know, but you have a different region that becomes maybe chaotic. Here, what I've done is colored the not empty sets to show you the clusters. So the spatial clusters are very important in all these ideas. And a cluster is simply a sequence of connected cells. So cells that are occupied, that are connected, right? So you could walk from here to any point in the yellow just by going north or south. Or south, yeah, no, north or east. And so like a cross, right? You cannot go in diagonal. So these are the clusters, and I'm going to talk a lot about clusters from now on. We see that all these clusters, they span the system, right? Because you can go from this end to the other in the yellow. Not all of this, right? This one doesn't, right? But the spanning clusters will play a critical role. All right, and then if you run it for more time steps, then you start getting these really patterns that are reminiscent of maybe growth of some sort of plants, right? And that's your fractal right there. This is the fractal, right? You see the Sierpinski triangles arising, and hopefully, right? So, and again, I mean, this particular rule might be predictable to your left, but in the right side of it, it's very unpredictable. Okay, so that's the same rule with the different initial conditions. So just like a random 0, 1 of the first row, and then you run it. All right, and then I think the next slide will show a time space diagram of the I-24 project corridor in Tennessee. Hopefully you guys are familiar. In a sentence, just the largest scale microscopic data, actual data that we have. So trajectory data, I think, is a 6-mile corridor. Now this is, I took a picture of their presentation the first time they put, when I saw these pictures, I went. So here's the time space diagram. Space goes that way, sorry, and times probably goes that way. But the point I want to make, and these are vehicle trajectories, for example. The point I want to make is the resemblance between the two. Yeah, and this is just a conjecture. It's not even published or anything. But so this is rule 30, right? And it might have something to say about freeway traffic, right? These are the stop and go waves that you see in the freeway. And there's entrances and exits that's 6.4 kilometers. And it's the largest that we have so far. And this individual trajectory data is just absolutely amazing. And this is how, waves propagate, all parallel, and they grow at the beginning because there might be on-ramps and off-ramps, well, on-ramps most likely. But the surprising fact is that so much similarity with that. So that's our next, one of the next ideas to explore. All right, these are the 256 cellular automatas, starting with a single occupied cell. So some are very boring, some are not so much. You see a lot of fractal patterns here, right? Surface triangle there. 184 is traffic, very boring. That's traffic. But yet is critical, and it has all these amazing things. All right, so this is, again, very boring. You start with a single vehicle, it just goes at the free flow speed, right? It advances one cell at a time. Kind of boring, yeah. We can do the opposite. Start with a full freeway, a jam, except for one spot, right? And this is what happens. It's kind of the opposite, right? So we say that there's a symmetry between free flow and congestion. They're the same model, right? It's just a particle going at maximum speed, right? And yeah, that turns out to have big implications of simplifying models. Okay, do the same experiment. What we start, instead with a single occupied cell, we start with a random initial conditions. So random 0, 1. Near the critical density, which is again 1/2. So critical density is when you have, half of the spots occupied. All right, so it's the same picture I showed at the beginning with the stop and go waves kicking against traffic and everything, right? So this is 184. That's the model we use for traffic. Now, if we run it more, we start seeing kind of the spikes, right? So reminiscent of crystal growth, and also compatible with the data that I just showed you in the sense that waves just propagate at a constant speed against traffic, no matter what, right? You see it here. Okay, so it captures the essence of traffic. All right, and yeah, the spikes are reminiscent of crystal growth. So I want to take a look of crystal growth models. Maybe they have something to say about traffic as well. There's a surprise here. So when I ran rule 99, I obtained this pattern. And I'm hoping, I mentioned this to you, right? Yeah. Did you figure it out yet?
No.
Yeah. So I think this rule should be able to simulate the process of on-ramps. It looks like they're filling up. Yeah, it's like you start with a low demand, maybe, and the freeway start filling up, and this might be a correct model to do that. But again, it's a conjecture. All right, and then let me go back to self-organized criticality. Let me explain what it is first. So yeah, let me talk about the sand pile model. It's very simple, and you can read this. Self-organized criticality is a property that traffic flow has, and it's best explained like with the sand pile model. So imagine we have a table and we start throwing grains of, could be anything, really. Yeah, grains of sand, right? And at some point, you're going to reach the critical slope. So there's going to be enough, and then you put one more, and you're going to have the avalanche. And the avalanche is like would correspond like a congestion event, right? A shock wave going back, right? And of course, the grains of sand would be maybe the cars that go into the system, right? So this idea of reaching the critical point, right? And then you're in a state of limbo. You don't know when the collapse is going to come. It's like you don't know when the earthquake is going to hit, right? You don't know when the stock market is going to crash. But you're in that state, right? And you keep throwing sand and sand, and it's impossible to see when the avalanche will come. It's impossible because it depends on the position of every little grain inside the pile, right? There's a lot of history in that system, right? And that's why it's unpredictable. Because you'd have to know the exact history, right? So it's not just about the initial conditions in the traffic problem. In this case, it would be the initial conditions plus the history that you would have to know perfectly, right? And that's why we cannot predict this thing. Okay, so when you look at the sizes of the avalanche, you find these power laws, right? And they're coming. They're power laws with the same slope. It's 1.2, I think. Right, so that's a very simple example of this self-organized criticality thing. Now, in this paper, I showed that I gave like the theoretical reason why it should be the case. Let me just give you the intuition. All right, so this is the same types of time-space diagram we're been looking at. It turns out that the traffic flow problem could be, let's say, streamlined in that if you want to see what happens at any given point, you have to solve a minimum path problem. So you want to start here, and you ask the question, what's the minimum path to reach the boundary? All right, and then you can go at these two speeds only, right? So there's infinite number of paths, right? And the minimum path will give you the solution you're looking for. So it will give you the traffic flow at that point, right? All right, so what happens at the critical density is that the cost of all those paths is the same. So it doesn't matter which one you choose, which path you choose. They're all going to have the same cost, and that cost is going to be this random walk that you see here. All right. So at the end of the day, what happens is this: that so for this point P here, where is the back of the queue? So the jams stopped right here. And if you ask the question, what is the duration of that jam, right? So the lifetime of a stop and go wave propagating, then the answer would be is half of this distance. And you can see it, right? That's the duration h here. And it turns out that this distance, and because this is a random walk, it's known as the return time of a random walk. So you're at a certain level, and this is, a coin toss. It's a random process, but the time until it reaches the same level is what gives the duration of the jams. All right, and it's known from the random walk theory that time is a power law. Right, it's going to be a power law with exponent 0.5, and sure enough, with our numerical experiments, we find a slope right in the same vicinity. Okay, which shows that the simplest model, right, the 184, with no determinism, is able, or rather exhibits self-organized criticality, right? Because of this power law, and because this is in a critical state, right? We're at the critical density there. Okay. Yeah, and that's really why it's such a complicated problem, is because of the slope, where, as I said before, there's no mean or variance. Okay, and the other thing I like about this picture is that you really see the fractal here. So fractal is one way of recognizing a fractal is if you zoom in, you keep seeing the same thing. Right? So here you zoom in, you zoom out, you see the triangle, but then you zoom into this triangle, for example. So statistically, the small one, this little triangle, is the same as the big one. right? And then you keep zooming this little triangle, and you know. So you zoom and you zoom, you see the same thing. That could be interpreted as a fractal plane. Now, this could be leveraged, right, in our methods, and that's what we're looking for now. If it's really a fractal, you could only analyze a little portion here and then extrapolate, maybe scale it up with the appropriate exponents. That's one possible application. Okay. Now, at the end, I mean, at the beginning, let's say the prime culprit of this problem is our willingness to drive fast, right? It's because we want to drive as fast as possible that the system reaches the critical state naturally, right? Which is the defining concept for self-organized criticality. All right, and I think I might leave it at this point. So I have maybe a few questions.
Thank you.
All right. Thank you. Thank you. Oh, these ones? Yeah. Right. So this is called finite size effects. And it means that, so here the size of the system is just the size of the road, right? And here maybe the road was comparable with 10 to the 4, right? Now, if you chose a thing, a length of 10 to the 8th, you would see the same line, but then at the end, you would have this drop. It's because of the finite system, you're not able to observe what the rest of this line, right? But if you keep increasing the size, you would. Or you could decrease it, and then you would see a line until here, and then the drop. Yeah.
I had a similar issue with similar network.
Mm.
Now there's a size of clusters.
Right.
Yeah, when I try to draw a straight line, you always have some.
Yeah, there's
what
always
looks like outliers. I was deciding whether I should keep them. Yeah.
Right.
I explained if it's depending on the size.
Right, and what people do there is, so you run it for different sizes, and you keep track of this breaking point, and you would see that the breaking point scales as a power law of the system size, and that exponent is going to be like a critical exponent. Yeah.
What about implications? What about implications for the situations like we have already passed the critical density? I mean, here in the free flow, we can say that maybe our willingness to drive as fast as possible is not good. That's do more harm than good. But what if in we're already in a congested state?
Right. Next question. If it's congested, right? Yeah, it does go to the critical point, right? It's a rarefaction fan. Remember that?
It's curious that the data you present, especially the one from TTI, the delayed data, we don't really know which densities are those data collected from. I mean, it's likely they are collected from very congested scenarios and free flow scenarios. But the results, or if you look at the exponent, it seems they will align well with the theoretical findings at the critical density, where the demand and supply may match.
Right.
Yeah, that's also, I cannot explain, but.
This one, right?
Yeah.
Yeah. So you're asking about what the traffic conditions?
Yeah, we don't know that, right?
They're probably annualized. So it's like they take all the data, during critical and non-critical periods.
Or does it imply actually that the real data, actually they are at some point, meaning the demand and supply, they're quite close. Otherwise, we would not see
scaling.
Yeah.
Excellent question. Excellent question.
When I simulated the congested networks, I can see very different exponents. If you impose different density levels.
All this theory is at the critical density. Right. And very free flow, very congested. Yeah, it's not going to apply. But you're saying that somehow it does.
Yeah, especially this one.
Yeah, maybe the critical state dominates. Maybe. Maybe our cities are congested the whole day. But yeah, good point. It'd be nice to break down the data and critical and non-critical. All right. Thank you for your attention.
Last chance, any question or comment? And I know that this topic is very interesting, and it's like Dr. Lava give us a very new perspective of looking at the traffic flow. And, okay.
Yeah, thank you again for presentation and a new topic, a new way to analyze traffic management. So my question will be how you determine that your model using criticality will be significant for traffic management, the relationship between these kind of modeling and traffic management. What is your criteria, I would say?
Yeah, it's very simple. It has to be microscopic. That's it. As long as it's micro, and it doesn't matter which model you use, really. At the end of the day, all that matters is that two vehicles don't occupy the same space at the same time. Just collision avoidance. Any model that has that is going to have criticality and all these things. So yeah, then my suggestion is just to use the simplest, right? Don't waste your time in the details, right? Which is another big consequence of this is that, and it comes from universality. It tells you that the system, the type of questions we've been interested here, the answer to those questions doesn't depend on the details. If it's autonomous or not, or what the headway setting was, or how people negotiate intersections, none of that matters. You have congestion in the network, everything goes away. All that matters is that people do not collide. Because that's how space gets, that's how waves spread, right? Because people have to stop. And now the precise way in which people react to that doesn't matter. Does not matter.
So your idea is that, so we create a simple rule.
Yeah.
And we analyze the network, and with that simple rule, we can interpret.
Yeah, 184. 184 is the simplest, fastest traffic model. But yeah, then you need to add the lane changes, and then yeah, you would have to use a lane changing model. Yeah, and then, but yeah, if you had to choose one, choose the simplest. If you already know one, just keep using that. I mean, it's really not important what the traffic model is. For these type of questions, these are big picture. Now, you're concerned about the minutia, the day-to-day, right? Yeah. I would stay away from those questions because they're not answerable, right? But yeah, you would have to do it, right, for your. All right. Thank you very much for attending. Thank you.